Welcome to this tutorial on access control lists, also known as ACLs. Our primary goal today is to master the core concepts that are required for implementing access lists. To achieve this, we will begin by discussing the importance of ACLs and what purpose they serve. From there, we will cover some of the key terminology and explain the different types of ACLs available. Lastly, we will dive into the actual configurations and syntax used to implement access lists. At the conclusion of this tutorial, you'll have a much greater understanding of the topic, and you'll be well on your way to becoming an ACL wizard. So what exactly are access control lists? An ACL is basically a filter that can be applied to the interface of a router and even some switches. As a filter, its job is to analyze data passing through the interface and either permit or deny entry based on a set of criteria. You could say an ACL is sort of like a bouncer guarding the door to a popular club. As the stream of people attempt to gain entry, the bouncer checks a list to see if they meet the required criteria. If a person passes the test, they're allowed into the party. If not, they're kicked to the curb. The same idea can be applied to packets attempting to pass through the interface of a router. This ability to filter packets make access lists a powerful tool for network managers. ACLs are primarily used for security purposes. For example, a manager can limit access to sensitive material located on a server. A manager could also deny certain services, such as Telnet or FTP. Access lists can be simple and broad, like in the case of blocking a network from reaching another network, or they can be more complicated and specific, like permitting HTTP access to a server for one particular host only. Whatever the intended purpose of an access list, there are a few rules we must consider before implementing one. First, each criterion or line of an access list is applied to a packet in sequential order. This is important because once a packet matches a line on the list, the packet is either permitted or denied without any further consideration. In addition to these two rules, there is an implicit deny statement at the end of every ACL. This invisible statement means that if a packet doesn't match any of the criteria in the list, it will be thrown out. For this reason, it is very important to remember that every access list you create should contain at least one permit statement, or it will deny all traffic. And this, of course, would defeat the purpose of having a list in the first place. Now that we have the basic rules down, let's look at some of our options for choosing the right kind of ACL for our needs. There are two main types of access lists that we can build from. The first is called a standard ACL. The only kind of criteria that can be used for this type of ACL is a source IP address. In other words, a packet is accepted or discarded based solely on its source address. Because of this, standard ACLs are very limited in their capabilities. They can't distinguish between different types of traffic and therefore permit or deny an entire suite of protocols. Due to these limitations, standard ACLs are a less desirable option for most scenarios. For more advanced control, an extended ACL may be used. This type of access list can apply a variety of criteria with which to evaluate a packet. Options include source and destination addresses, protocols, and even specific services. For situations that require precise restrictions, extended ACLs are the preferred option due to their greater flexibility. After determining which type of access list to use, we must then decide how to identify it. Again, there are two options for identifying ACLs. The first is a simple numbering scheme. For a standard access list, ranges 1 through 99 and 1300 through 1999 are available. An extended access list follows the pattern by using ranges 100 through 199 and 2000 through 2699. The second option for identifying ACLs is to choose a descriptive name. Named access lists can be more helpful in bigger networks that utilize a large number of ACLs. Using a descriptive name makes it possible to quickly determine the identity or purpose of an ACL without trying to decipher the lines within the list. Another benefit of using a named ACL is that it gives us the ability to insert, delete, or edit individual lines in the list. These features tend to make named ACLs the more appealing option. Once we have created an access list, we must complete the final step of applying it to the router interface. In order to apply the list correctly, we have to answer a couple of questions. First, which interface should be used? There are two general rules of thumb when making this decision. For a standard ACL, we should apply it as close to the destination as possible. This ensures that the ACL will only block traffic attempting to reach the destination. If we instead place it close to the source, it would block all packets sent from the source. For example, let's consider the following topology. In this scenario, we have three networks connected by two routers: the 1 network, the 2 network, and the 3 network. Let's say we want to block host A in the 1 network from pinging host B in the 2 network. Host A would be the source, and host B would be the destination. Since this is a standard ACL, we need to apply it as close to the destination as possible. Therefore, it should be applied to the FA01 interface on the R1 router. If host A attempts to ping host B, the packets will travel through the switch to router R0, then across the network to router R1, where they will be blocked as they attempt to exit the FA01 interface. On the other hand, if we place the standard ACL close to the source at the FA01 interface on router R0, it would prevent all traffic originating at host A from exiting the network. For this reason, it's very important to place a standard ACL as close to the destination as possible. For an extended ACL, we should apply it as close to the source as possible. Since extended access lists can be very specific, we are able to filter the designated traffic soon after it leaves the source. This prevents unwanted traffic from using up bandwidth as it travels across the network, only to be denied at the destination. Looking at our sample topology again, let's say we would like to deny host A from having FTP access to host B. Since this would require an extended ACL, we need to apply it as close as possible to the source, which would be the FA01 interface on router R0. If host A attempts to establish an FTP connection with host B, the packets will be denied as soon as they reach this interface, preventing them from traveling across the network. This is acceptable because we are only filtering FTP. All other packet types originating from host A will be permitted to leave the network. The last question we need to consider before applying an ACL is which direction of traffic should be filtered. At any given interface, traffic can flow in two directions: inbound or outbound. When considering direction, we must view it from the perspective of the router. Inbound traffic is traffic coming into the router. Outbound traffic is traffic exiting the router. Let's consider traffic passing through router R1. Any traffic leaving the 2 network must pass through the FA01 interface. Since this traffic is coming into the router, it is considered to be inbound. Likewise, any traffic that is destined for the 2 network must also pass through the same interface. However, since it is exiting the router, it is considered to be outbound. Once you have determined the type of ACL, the interface, and the direction, you are ready to begin writing an access list. Using the same topology, let's create a standard, numbered ACL to deny host B on the 2 network from accessing host A on the 1 network. All other traffic will be permitted. Since the targeted traffic is originating from host B, it is considered to be the source, and host A is considered to be the destination. With a standard ACL, we will need to place it as close to the destination as possible. This means we will apply our list to the FA01 interface on router R0. Because we are trying to block the traffic as it attempts to exit the router, the list will be applied in the outbound direction. We will begin by entering global configuration mode on router R0. The first step is to use the access list command followed by a number in the standard range. Recall that as a standard ACL, we can only filter based on a source IP address. In this case, it will be the source address of host B. So we will then deny host 192.168.2.100. This completes the first line of our list, which denies host B from reaching host A. For the next line, we will add another statement permitting all other traffic. Remember that there is an implicit deny statement at the end of every list, so if we do not have at least one permit statement, all traffic will be denied. Now that we have created our list, we need to apply it to the FA01 interface. To do this, we use the IP access group command followed by the number. Lastly, we need to specify the direction the traffic will be filtered, which will be outbound. At this point, we have created a standard ACL that blocks host B from reaching host A. We can verify our list by using the show run command. From here, the list can be seen on the Fast Ethernet 01 interface. The rules of the list can be seen further down. Let's go ahead and test the ACL by attempting to ping host A from host B. We get a reply from the router stating that host A is unreachable. Now let's try the same from host C. The ping was successful, so we know that our standard ACL is functioning properly. So far, we've demonstrated how a standard numbered ACL can filter traffic using a source IP address. As discussed earlier, due to its limitations, this type of ACL is not ideal for most situations. So let's shift our focus to extended access lists, which provide much more control over the network. Extended ACLs are constructed in a similar way to standard ACLs, but there are some differences to consider. An extended ACL still filters based on a source address, but also uses a destination address as well as an optional port number or service. The format of an extended ACL follows a pattern that can be used when writing your lists. First is always the access list command containing the keyword along with the name or number. Next is the permit or deny keyword, followed by the protocol. Then we list the source and destination addresses. Note that if we are referring to a single host with either the source or destination, we can place the host keyword before the address. If we are referring to a range of hosts, we instead place the wildcard mask after the address. Lastly, we identify the port or service with the EQ keyword. Memorizing this sequence can make it much easier when writing extended ACLs. With the extended format in mind, let's take a look at a new topology. Here we have the one network in yellow, the two network in blue, the three network connecting the routers, and the four network in green. In this example, we will use an extended access list to place limitations on the blue network. The blue network needs access to the entire green network, as well as HTTP access to the web server on the yellow network. All other access to the yellow network will be denied. As an extended ACL, we know that it should be placed as close to the source as possible. Since we are filtering traffic coming from the blue network, it is considered to be the source. This means the list should be applied to the FA01 interface of router R1 going in the inbound direction. To create the list, we will enter Global Configuration mode on R1. First, we will permit HTTP access to the web server. Using the access list command, choose a number in the extended range. Next, permit the TCP protocol. Then identify the source, which would be the network address for the blue network. In this case, we are permitting an entire network, so we will use the wildcard mask after the source address. Next, identify the destination. Because we are only permitting access to a single web server, we can use the host keyword before the address. Finally, identify the desired port or service. Now we will permit access to the entire green network using the same ACL command. This time, permit the IP protocol. Identify the source and the destination. Again, since it is more than one host, we will use the wildcard mask. That takes care of our permit statements, giving the blue network access to the green network and HTTP access to the web server on the yellow network. Recall that at the end of every ACL is an implicit deny any statement. Because this statement is already configured, we do not need to add any additional statements in order to restrict access to the rest of the yellow network. All that remains is to apply the ACL to the FA01 interface. Use the IP access group command, followed by the list number and the direction, which should be inbound. Now that our ACL is complete, we can verify it using the show run command. The list can be seen on the FA01 interface, and the details can be seen further down. To test the ACL, let's use the web browser on host B to access the address of the web server on the yellow network. The browser is able to load the page. However, since we only permitted HTTP access, we should not be able to ping the web server. If we do attempt to ping the server, we receive a message from the router stating that the destination is unreachable. Now let's check to see if we have access to the green network by pinging host E. We receive a reply from host E, so we know that our extended ACL is functioning properly. At this point, we have covered numbered ACLs for both the standard and extended options. Now let's take a look at how to configure a named ACL. Named access lists can be used for both standard and extended ACLs. From a functional standpoint, they perform exactly the same as a numbered ACL. The primary difference is that they are identified by a name rather than a number. This can make it easier to manage a network containing a large number of ACLs. Configuring a named access list is slightly different than a numbered. Instead of beginning the command with the access list keyword, we use the IP access list keyword. Then we must specify whether it will be standard or extended. Lastly, we choose a descriptive name for the list. After entering the first line, the router prompt changes. This denotes we are now in named access list configuration mode. From here, we can enter permit and deny statements. Once the list has been created, we finish by applying it to an interface in the same way as before. Now that we're familiar with implementing ACLs, let's discuss some of the tools available for investigating and verifying access lists. These can come in handy when verifying your own ACLs or when checking for ACLs that someone else has created. As demonstrated in the previous examples, the show run command can be used to verify an access list. This command shows ACLs on specific interfaces as well as the parameters. This works well for simple networks, but as a network grows in size and complexity, the show run output can become very lengthy and cluttered. In these instances, a better option would be the show access lists command. This command shows all ACLs configured on the router, including their parameters. It also provides statistics about how many times packets were permitted or denied. Place the name or number of an ACL at the end of this command to show only the specified list. The drawback to this command is that it does not reveal which interfaces the ACLs are located on. To find this information, the show IP interface command can be used. This will display which interfaces have access lists applied to them. A specific interface can be added to the end of the command to show a single interface at a time. Using a combination of these show commands, we can effectively monitor and manage all of our access lists. As promised, you are nearly an ACL wizard at this point. With a little more practice, you'll be there in no time. Thanks for watching and good luck with your networking endeavors.